So this is just going to be a quick video on explaining effective nuclear charge, how to calculate it, what shielding means, and essentially preparing to use effective nuclear charge as an explanation to the observed trends that we see in the periodic table. So you will see effective nuclear charge sometimes referred to as core charge, and if you discuss periodicity with your friends and colleagues in Year 11 who do VCE, they will probably refer to this as core charge. In IB, however, you will more regularly, and you should try and use the term effective nuclear charge. And essentially what this is it's the experience of the electrons, the outermost electrons, how much they are pulled towards, or the attractive force that they feel towards the nucleus of the atom itself. Okay, so it is the charge that is experienced by the outer shell electrons. So if we have our electrons out in the valence shell, okay, so, and we're talking about an electron out here, it is how much, given that our nucleus is positively charged, how much of this attractive electrostatic force that this electron feels. Okay, so it is determined by subtracting the number of inner or core electrons from its atomic number. So often you will see it referred to as ZF, but effective nuclear charge is equal to the atomic number minus the shielding electrons. Okay, and this is because we're talking about neutral atoms, so the atomic number is going to be equal to the total number of electrons, or in this case more likely the positive charge in the nucleus. Okay, so this is the positive charge in the nucleus. This is the electrons that are between the valence electron or the valence shell and the nucleus. Okay, if you think about what shield means to block or protect something. So when we look at this, electrons within this shielding range are also going to have a negative charge, so they will be repelling. They'll be repelling the other electrons, which will reduce the amount of attraction that this electron feels towards the nucleus. Okay, so the inner shell electrons shield the valence electrons from the full positive nature of the nucleus, which results in a reduced attraction. So the more shielding electrons we have compared to our atomic number, the less attraction to the nucleus that our electron will experience. If we look at examples that we have here, which is beryllium, magnesium, and calcium, we can see that for beryllium we have a +4, we have an atomic number of 4, so we have 1s2, 2s2. Our valence electrons are going to be in the second shell, so between these valence electrons and the nucleus we have this first shell. So there are two shielding electrons between the nucleus and the valence shell electrons. So we're going to have 4 minus 2, which means that every valence electron is being pulled towards the nucleus with a +2 charge effect. If we look at something like magnesium, we will notice that this also is going to have, we have an atomic number of 12, okay? It's going to have 1s2, 2s2, 2p6, 3s2, okay? So these now become my shielding electrons. I'm going to have 12 minus 10 is going to be +2. Calcium, we've got 1s2, 2s2, 2p6, 3s2, 3p6, and then we are going to have 4s2. So 4s2 is now my valence shell. All of these 18 electrons are my shielding electrons. I'm going to have 20 minus 18 is going to leave me with a +2 effective nuclear charge. if you look at these, we can see they all have a +2 effective nuclear charge, and that is because they are all elements in group 2 of the periodic table. Okay, so as we go down a group, our core charge is consistent. It changes, however, as we move from left to right across the periodic table because our core charge will increase. We can see that with sodium and chlorine as an example. Sodium's group 1, we have 1s2, 2s2, 2p6, 3s1 because it's number 11. So this is going to be my valence shell. These 10 are going to be my shielding. So I'm going to have 11, which is my atomic number, minus 10 shielding is +1. If we continue across period 3, what we will see is that we're going to increase our atomic number by 1 each time, but our shielding electrons won't change, okay, because we're going to keep adding electrons into this outer shell. So the effective nucleus charge of any one of these valence electrons will increase by 1 as we move across the periodic table from left to right. So that by the time we hit chlorine, we're now at 17, 1s2, 2s2, 2p6, 3s2, 3p5. We now have 3 is our valence shell, okay? There are 7 electrons in my valence shell. I have 10 electrons that are between my valence shell and my nucleus. So my atomic number, which is 17, minus my 10 interior shielding electrons, is going to leave me with a +7 core charge. So group 7 is going to be +7. Group 1 is going to be +1. Okay, so the group number, just the same as the number of electrons, corresponds to my effective nuclear charge. While you can remember that, and remember that your effective nuclear charge increases from left to right and is the same down a group, okay, it is important to be able to calculate your effective nuclear charge when comparing two atoms and using this to explain the properties. Many of the properties that we see in terms of physical properties, melting points, size, and things like that, as well as our chemical properties, can be explained using effective nuclear charge. And when doing worded questions involved with periodicity, this is something that we should certainly be doing. We should start with our electron configuration, work out our effective nuclear charge, and then explain how that affects the properties. And we will look at the properties in our next video.